Okay, so resuming on our discussion of electron configurations, let's look at the electron configuration for bromine as it really showcases something quite important. So bromine is a 7A element. It also, looking in the periodic table, would someone like to tell me what is bromine's atomic number? What is bromine's atomic number?
35.
Yep, exactly right. So then we'd have a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So we've used up 10, 20 electrons. And what orbital is filled? What subshell is filled after the 4s?
3p.
Yep, exactly right. And the 3d orbital can hold 10 electrons. So we used up another 10 electrons. We have 5 electrons remaining. So how many electrons go into our 4p orbital?
5.
Yep, exactly right. Now, if you wanted to write this as an abbreviated configuration, we can summarize these initial core electrons using the configuration of the preceding noble gas. So this could also be written as argon 4s2 3d10 4p5. Now there are a few things to note here. First, you cannot include these 3d electrons in argon's noble gas configuration. These 3d electrons and the 3d orbital is filled after argon. Further, which of these electrons are valence? Which of these electrons are in the outermost orbital with the largest n value?
4s2 and 4p5.
Yep, exactly right. And if we add up our valence electrons, we see that we have 7 valence electrons. These 3d electrons are core electrons, and they aren't as accessible for chemical reactions. Does that make sense to everyone? Any questions on this example?
Which ones are we adding for the 7 valence electrons?
The electrons in our outermost orbitals, which are our 4s and 4p orbitals, because they're the orbitals that are farthest from the nucleus with the largest n, and so these are called our valence electrons. We don't add our 3d electrons because they're inner shell. They have a smaller n value, and they're held correspondingly relatively closer to the nucleus.
Oh, okay. So the 5 and the 2 is where we
Yep,
get the
exactly.
7. Thank you.
So let's look at another set of examples, and this one's a little bit, this next set will be a little bit more straightforward. We're asked to write the configurations for each set of ions. Now for ions, you need to be really careful when you're counting electrons. So for example, for O2 minus, oxygen, if we look in the periodic table, if we go and find oxygen in our periodic table, it typically has an atomic number of 8. However, since we have a 2 minus charge, our number of electrons is equal to our atomic number minus the charge, which gives us 10 electrons to work with. So if we find our closest preceding noble gas, that would be helium. And then we fill in our orbitals from the lowest to the highest energy. And as we notice, the configuration for O2 minus matches the configuration for that of the noble gas neon, which is helium 2s2 2p6. So one thing that we've noticed, one common trend that we've noticed in our discussions is that many common ions adopt an electron configuration matching that of the closest noble gas. So noble gas notation or abbreviated electron configurations are really important because they can help you very readily see patterns of reactivity and patterns for ionization. So what I'd like you to do is I'd like you to look at the following 3 cations, and I'd like you to propose an electron configuration for each of the 3 cations. Note, just for completeness, I'd prefer that you write out the noble gas configuration following, I'd like you to write out the noble gas configuration identifying the core and valence electrons, because noble gases being 8A elements will have 8 valence electrons. It's generally not appropriate to just put the corresponding noble gas symbol in brackets. It's sometimes seen when people are writing electron configurations for noble gases, but I'd prefer you write out the noble gas electron configuration such that the core and valence electrons are clearly shown. So let's take about 4 to 5 minutes and let's work through this example, and then we'll come together as a group to discuss. And if you have any questions in the meantime, don't be shy to ask them in the chat or verbally. Additionally, if you have any proposed responses, don't be shy to share them in the chat or verbally. And we'll discuss this example in about 4 to 5 minutes. And let's try to get a few proposed electron configurations in the chat. You may notice many of your electron configurations will be very similar when you're writing the configurations for ions and for species with noble gas-like configurations. And don't be shy to share your responses in the chat or verbally. Or if you have a question, I'd be happy to address any questions as well. And don't be shy to share your responses in the chat or verbally, or ask a question. And we'll discuss this example in another 2 to 3 minutes. And let's try to get a few more responses in the chat before we discuss. And we are starting to see a reasonable pool of responses in the chat. Let's keep working on this and we'll discuss in about another 1.5 to 2 minutes. And as I notice in the chat, students are starting to see that some of these ions have the exact same configuration. And so we have a nice pool of responses. Let's add a few more responses to the chat and we'll discuss in about another 30 seconds to a minute. It's great that I see this pool of responses in the chat and of participation from a wide swath of the class. Okay, so let's discuss. So sodium in the periodic table has 11 electrons to its name. Sodium plus, however, we have to take our atomic number and subtract the charge, which is +1, and that gives us 10 electrons to work with. Filling our orbitals from lowest to highest energy, we have 1s2, 2s2, 2p6, which could in turn be written as helium 2s2, 2p6. If we have a 10 electron structure, it will have the exact same configuration, same number of electrons, same configuration. Does that make sense to everyone? Okay, let's look at aluminum. Would someone like to tell me what is the atomic number of aluminum? We need that to calculate the number of electrons. 13. Okay, so for our number of electrons, we have 13 minus a charge of +3. We have 10 electrons. If we have the same number of electrons, will our configuration also be the same?
Yes.
Exactly right. So 1s2, 2s2, 2p6. And that gives us helium 2s2, 2p6. So as we can see, as we have a noble gas-like configuration, all of our electron configurations for these noble gas-like ions have 8 valence electrons. Let's look at lithium now. What is the atomic number for lithium? What is the atomic number for lithium? 3, okay. But since it's lithium plus, our number of electrons is 3 minus the charge, which is +1. That gives us 2 electrons to work with, or a configuration of 1s2. Does this make sense? Any questions on these examples? So writing the configuration for ions is pretty straightforward compared to neutral atoms. You're often going to notice the configuration for most ions are going to be almost identical. Okay, so let's talk about valence electrons now. Valence electrons are best defined as electrons in the outermost energy level with the largest N value. The valence electrons are also equal to the group number for main group elements. Further, and this is really important, elements of the same group in column, in other words, have the same valence electron configurations and number of valence electrons. And these valence electrons are really important because they're the electrons that are actively being exchanged, gained, or lost in chemical reactions and bonding events. So as a result, elements of the same group have similar reactivity because they have the same valence electron configuration and number of valence electrons. Does that make sense? Same column, same group, same or similar reactivity. So, for example, if we look at the configurations for each of our main groups in the periodic table, we notice that the only thing that changes as we move down the periodic table is that our orbital n value increases. The configuration of our valence electrons in each of our groups is the same within that group. Does everyone notice this clear pattern in the electron configurations and number of valence electrons? So for 1A, we have 1 valence electron. For 2A, we have 2 valence electrons. 3A, 3 valence electrons, and so forth. Any questions on this idea? Okay, so let's keep going and let's talk about isoelectronic species. We commonly see these when we start talking about the electron configurations for ions. So isoelectronic species have the same number of electrons and the same ground state electron configuration. So for example, if we look at each of these ions, sodium plus, F minus, N3 minus, O2 minus, what element are all of these ions isoelectronic with? What electron configuration or what number of electrons matches the number of electrons observed for each of these ions? All of these ions are isoelectronic with the noble gas neon, which has a configuration helium 2s2 2p6. Now this is really important because this can help us to understand a really important pattern in terms of ionization preferences. So just to make sure we're all on the same page, I'd like you to tell me what, oops, one moment. I'd like you to tell me what neutral atom is isoelectronic with H minus. So let's take a moment. I'd like you to figure out the number of electrons that H minus has, and I'd like you to tell me what neutral atom has the same number of electrons as H minus. And let's give everyone about a minute to a minute and a half on this example. And don't be shy to share your responses in the chat. So we're starting to see a pool of responses. So let's talk about this. So H minus. So we initially have 1 electron. We then subtract the charge of -1, and that gives us 2 electrons total. And the element with 2 electrons is helium. So H minus is isoelectronic, has the same number of electrons as helium. So it's isoelectronic with helium. Does this example make sense? Perfect, perfect. So let's talk about noble gases now. They're a really important group in the periodic table. Noble gases, which are group 8A elements, have full outermost valence shells and are more stable and less reactive than other electron configurations. Noble gas configurations, 8 valence electrons, are generally stable. There's one other noble gas configuration we need to be aware of, and that's the 1s2 configuration, which matches that of helium. Now, why is this important? Why does this matter? Well, it is more favorable for atoms to gain or lose electrons if you generate a stable noble gas configuration. Further, it's also relatively easy to lose high energy valence electrons or to gain electrons if you're creating a full outermost valence orbital. So the takeaway from this idea is that atoms will form ions with noble gas configurations. And as a result, atoms will prefer to form ions with their charge equal to the group number if it's a 1A through 3A element. In other words, if it's a metal. While atoms will prefer to form ions with charge equal to the group number minus, in other words, are non-metals. Essentially, we're trying to reach the closest noble gas configuration. So, if we look at aluminum, for example, aluminum is a group 3A element, and it's also a metal. So then its charge is equal to the group number, which is +3. To help you visualize why this is occurring, aluminum has a configuration of neon 3s2, 3p1. So how many electrons do we need to lose to get to neon? How many electrons do we need to lose to get to neon? Yes, 3 electrons, exactly right, because this configuration has 3 valence electrons that we need to lose. Does that make sense to everyone? Does this idea make sense that you're losing or gaining valence electrons to reach the closest noble gas? So let's keep going. So oxygen, which is a group 6A, which is a non-metal element, adopts the charge of 2-. Why? Remember, we said the charge preferred for a non-metal main group element is equal to the group number -8. So 6 minus 8 gives us a charge of -2. Does that make sense to everyone? To help you visualize this from the perspective of electron configurations, if we have 6 valence electrons, how many do we need to gain to reach 8 valence electrons? And to help you visualize this, so initially, I have 6 electrons. And how many do I need to gain to fill out my shell? I need to gain how many electrons?
2.
2, exactly right. And that gives us 8 electrons. Does that make sense? Is everyone comfortable with these ionization trends? Okay, so let's keep going and let's first start off by writing the abbreviated or noble gas electron configurations for the following ions. I'll start us off O2 minus. Oxygen has an atomic number of 8. 8 minus -2 gives us 10 electrons, and that gives us a configuration of helium 2s2 2p6, which matches the configuration for that of neon. So what I'd like you to do is take about 2 to 3 minutes and write the configurations for potassium plus and lanthanum 3 plus. And remember, start with your electron count and then go from there. And we'll discuss this example in about 2 to 3 minutes, and I'd like to see a few electron configurations proposed in the chat. And we're already starting to see some reasonable responses in the chat. Let's try to get a few more responses before we discuss. And this is really just getting everyone used to writing electron configurations for common ions that they'd see in this class. And for lanthanum, don't freak out that it's in the lanthanides. Just think about your electron count and try to find the closest noble gas. And we'll discuss this example in about another minute. Okay, so let's talk about this example. So potassium, if we look in the periodic table, has an atomic number of 19. To calculate the number of electrons, we take the atomic number minus the charge, which gives us 18 electrons. The closest noble gas with 18 electrons would be argon, which has the configuration of neon 3s2 3p6. Does this first example make sense? So for lanthanum, just counting electrons, has 57 electrons. 57 minus plus 3 gives us 54. The noble gas with 54 electrons is xenon. And xenon has a configuration of krypton, 5s2, 4d10, 5p6, which matches the configuration for xenon. Does this make sense to everyone? Perfect. So what I'd like us now to do is I'd like us to look at the following set of atoms, and I'd like you to predict the preferred charge. So I'll start us off and I'll do one of the more tricky examples. So scandium has a configuration of argon 4s2 3d1. So to reach our closest noble gas configuration, we need to lose 3 electrons. So then scandium will prefer to form scandium 3+. So with that representative example in mind, and with the shortcut equations that I've showed you for predicting charge, I'd like you to predict the preferred charge for ions formed from the following 3 atoms. And we'll discuss this example momentarily. And make sure to note whether the charge is positive or negative. And let's try to get a few more responses in the chat, and we'll discuss this example in about another 2 to 3 minutes. And we're seeing a lot of reasonable responses in the chat. Remember that metals prefer to form cations with a positive charge, while non-metals prefer to form anions with a negative charge.
Professor, how did you get to 3D1?
Because the next orbital that's filled after the 4s is the 3d. And because scandium has 21 electrons and argon has 18, our 3 electrons go first in our 4s and then afterwards into our next highest energy orbital, which is the 3d orbital.
Okay, got it.
Does that make sense?
Yes, I didn't realize, I was counting up to 20, so I didn't realize it's 21.
No problem, no problem. Let's try to get a few more responses in the chat for the predicted charges of each of these ions, and then we'll discuss in about another minute.
Professor, how do we predict the transition elements? We just
The transition metals have their own set of rules, and the transition metals can adopt typically a variable charge. However, for most of the early transition metals, you can lose all of the 4s and 3d electrons to generate an ion. That's why I showed the scandium example, because it's a slight exception to the rules that we've discussed. So I wanted to make sure that the examples that I have you work on independently are more common charge prediction and electron configuration examples. Did that answer your question?
So we count to see if it's easier for them to gain or easier for them to lose. That's how we know if they
Exactly.
become cation or ion.
Yep, exactly right. And transition metals form cations, but they can lose a varying number of electrons. And we'll actually talk about that in the next chapter, how to handle transition metals and how to describe transition metals so that the reader knows the charge of that transition metal. So long story short, for transition metals, you can either lose all of your 4s or 3d electrons, but transition metals can form a range of ions.
Okay, got it. Thank you.
So let's discuss this example here. So phosphorus is a group 5a element. Just to make sure that we have a nice reference to go off of, has a configuration of neon 3s2 3p3. So using our formula, our charge is equal to the group number, which is 5 minus 8, which would be minus 3. So we'd predict that phosphorus would form the ion phosphorus 3 minus. Why is that? So in order to reach the noble gas configuration for argon, which is neon 3s2 3p6, we'd need to gain a total of 3 electrons. Does this first example make sense? Does this first example make sense? Looking at aluminum, it's a group 3a element, which means it's a metal. So it would prefer to form a charge equal to the group number, which would be positive 3. Why is that? Aluminum has a configuration of neon 3s2 3p1. So in order to reach the configuration of the closest noble gas, we would need to lose a total of 3 electrons. Does this make sense to everyone? Any questions on this idea? Finally, let's look at iodine. So iodine is a group 7a element, and it's a non-metal. So then we'd predict the charge would be equal to the group number minus 8, which would be -1. So iodine would prefer to form iodide, I minus. Does this example make sense to everyone? Everyone comfortable with predicting charge?
I'm kind of confused on how we got the 8 for that one.
So for non-metals, the charge preferred for a main group non-metal is equal to the group number minus 8. And this stems from the fact, so if we write out the configuration for iodine, it would be krypton 5s2 4d10 5p5. So we have 7 valence electrons to work with. And in order to go to the closest noble gas, which would be krypton 5s2 4d10 5p6, how many electrons would we need to gain? How many electrons would we need to gain?
1.
Yep, exactly right. And that's why we adopt a charge of -1, because we gained 1 electron during ionization. Does that make sense?
Yes, thank you.
Perfect, perfect. So we're at the end